and eventually it deforms to a ring, and then we can observe on this ring that some parts are more dense than the others, they have more ink, and those parts break off, and then they form new drops, and then this process repeats itself. To explain this phenomenon, we'll observe this problem from the drops reference frame, as in the picture. So, when the drop falls, water flows around it, and because of viscosity, water pulls outer layers of the drop of the ink with them, so they gain velocity, as in the picture. But those outer layers of ink also pull inner layers of ink because of viscosity, and we get like vortex motion inside of the drop. And it looks like this in the drop. We have two vortex motions, but as the drop falls, it flattens because of the drag force, and we would expect that this vortex motion is elliptical because of the shape of the flattened drop, but actually it is circular because it's more stable motion than elliptical. And this circular motion, like in this picture, causes flattened drop to deform to a ring, or a torus, to be more precise. And when the torus is formed, water flows through it and around it, and this causes the vortex to stop, because water that goes through the ring pulls ink in one direction, like in this picture, and that goes outside of the ring pulls the ink in the other direction, and that's the reason why the vortex stops. But if we take a look at the ring from the above, we can see that at some parts ink is more dense than the other, and the reason for that is that we can't assume that distribution of the ink will be uniform because of the chaotic motion of the fluids. And once there is more ink at one part, because of the cohesive forces, those parts will become even more dense. And because they are more dense, of course, they have larger mass, and bodies with larger mass tend to fall faster because drag force affects them. Effect of the drag force is lower for larger masses, so they fall faster, and then they form new drops, and then this process repeats itself. So we watch how water temperature and drop volume affect how many fragmentations happen. So how many fragmentations, not how many fragments we can see, but how many fragmentations happen. So why we chose these parameters. So we want diffusion of ink in water to be slow, because we don't want ink to just spread around the water. So we want this parameter tau to be as large as possible, where d in this equation is diffusion coefficient between water and the ink. And we also want this time tau 1 that tells us how fast does the vortex speed diffuse through the particle to be as small as possible, because vortex motion causes ring formations, and fragmentations happen from the ring. So we want this time to be as small as possible. And that's why we introduce this factor f, which is tau over tau 1. And we want that f to be as large as possible for fragmentations to occur. And if we use those equations and combine them, we can get this expression for the f. And there is some critical value of f at which fragmentation doesn't occur. And as we can see, f is proportional to the volume, v is volume of the drop, and it's inversely proportional to the temperature of the water. So we expect that for the larger drops will have more fragmentations, and for higher temperatures we will have fewer fragmentations. And we experimentally tried to prove this.
Yeah, this was our experimental setup. We used a big cup of water, and we waited some time for it to get still. Then we used different sizes of syringes. We measured the volume of the ink of one drop by dropping a large number of them, 10 or even 20 sometimes. I think it was even more in some cases. And then we looked at how much volume was depleted. And we measured the temperature with a thermometer. Then we observed how many times the thing that we had to explain or predict was not how many branches happen from one ring, but how many times the ring spreads. So how many generations of the drops there are. That's what we counted. We did a few measurements for each size and temperature, size of the drop and temperature, and we put most of the times it was the same number of branching, and we put that on the graph. So this is the three volumes we did it with. So the green circles are the smallest volume, the red triangle is the middle one, and the blue X is the largest. This is the temperature that we measured, and this is the number of fragmentations. So 0.5 is when sometimes the drop didn't spread at all, and sometimes it was once. For those that were like in between, we did a couple more measurements to be sure that it does vary, that our experiments aren't just wrong. I mean failures. And yeah, this is what we get. So for the largest volumes, we got as expected the largest number of branching. For the smallest, we got the smallest ones, and the temperature dependence is also as we expected. And we observed that the maximum number of branching we could get is 4. We never observed more than 4. So our conclusion is that our experiments did confirm our theory. So the number of fragmentations is lower for higher temperatures and larger for larger volumes. We also noticed some chaotic features of this effect. So when the volume is too large, the drop tends to just spread around in a chaotic fashion, not really making this ring at all. We try to explain this by just the fact that it's very unstable because of its size. It doesn't manage to hold together. And some methods we propose for the future is, our methods of measuring the volume might have been not very precise because it's hard to make the same drop every time. So if we could have some more sophisticated tools for measuring it, that would be great. Adding detergent reduced surface tension. Surface tension often made the drop just spread on the surface instead of falling down. Larger container would be great simply because we have more room for it to branch, and filming would be great too. And these are our sources.
Thank you.
What was reported by Team Croatia on problem number 3, ink tree. So the problem was very clearly leveled. you have to study this typical structure of ink falling into still water, and to determine the maximum number of ring divisions, and to see how it depends on the important parameters. And first of all, I'd like to remind that to define the terms, the reporters stated that it was to study the number of generations of water drops, so of ink drops. So that was just a statement, just to be clear about this. Now I have to sum out this very interesting and very good presentation. You made two parts, experimental and theoretical parts, and you studied the different size and volumes of the drop you injected into water. You also studied the temperature dependence of the water in which you injected ink to show that the number of generation decreases with the temperature. And you observe definitely how many times a ring can spread and fragment. And theoretically, it was a very clear and qualitative presentation. You studied the circular motion that causes drop to deform. You mentioned that there was cohesion forces and imperfect symmetry that causes fragmentation, and you studied the competition between fragmentation and diffusion. Then, well, the good points was that you studied the influence of two very important parameters, and you made a very clear qualitative explanation of what was going on at the beginning. Now, I have a few questions about this problem. You mentioned surface tension at the end, and it didn't appear before, and I think that perhaps this is something very important, or perhaps not, and I would like to know how, but you just mentioned it in the end, so it wasn't very clear to me. Also, I would like to know how experimentally you observed the fragmentation process, and first of all, the inhomogeneities that you mentioned, and the cohesive forces, how you did observe them, and how your theoretical explanation states with physical reality. Okay, and as for the important parameters, well, you study temperature, which is very good, volume, which is very good, but you put us a very interesting number, which is the F number, but F number depends on other parameters. It depends of the delta rho, so difference of density, and I'd like to know, and you didn't explore it so far. And what's more, you say that it's a self-similar process, but actually it's stopped to the end, so it's not exactly self-similar. So how does it vary from one step to the other? That I would like to know. And I'd like to add that you made no precise correlation, I mean quantitative correlation between your theory and well, your experience. So in order to discuss this, I have a few technical questions. I'd like to go very fast on this. Well, how did you first observe cohesion and inhomogeneities of the disk? And for example, what are the typical size of the inhomogeneities you observed? If you observe them. And then on the parameters, I'd like to ask you how you think that a density change would change to your results, and viscosity of water, of ink also. What is, this is, for me, this is quite important, what is the role of surface tension in this kind of phenomenon? Basically also I'd like to know about the speed of the drop, but this is less important. And most important, I'd like to clarify with you what consists in, what the fragmentation process consists in. I'd like to dwell on the homogeneities and the cohesive forces. I'd like you to explain to me what you mean by it, and how you could expect, for example, periodic rings, periodic fragmentation on a ring to happen. So if you don't mind, then well, we can begin discussing now.
First of all, can I answer these questions?
I'd like just very fast. How do you observe cohesion and typical size of homogeneities? How do you correlate what you said to what you said?
So the cohesion, it was more of a thing we learned from the articles.
But can you explain to me what you hear by cohesion? What is cohesion?
So the ink particles, they act on each other with intermolecular forces, and this tends to bring them together.
So this is basically viscosity, I think.
No,
because if you try to move one share of ink.
No, it's not. It's that if you have,
So they take together as a solid.
yeah.
More as a solid.
No, not as a solid. For example, when you, if you put a drop of, if you put a drop of water or anything on the table, it will not spread completely into one particle layer. It will go up into a.
Okay, so to me that sounds like a different name for viscosity. So let's call it cohesion or viscosity. So not a problem. But this is I think a good, interesting question. What is the typical size of inhomogeneities that you said that cause the fragmentation process?
Well, the point is that there are inhomogeneities because of the randomness of the.
Okay, so this is random. So this is perfectly random. In the beginning, this is random. So how can you have this torus, and you have random inhomogeneities like this?
Yeah.
Okay. So how and you have many inhomogeneities, and how can you go from this to this?
Yeah. Okay. So the point is that, for example, these two will will attract to each other, because this part is then more dense ink. It's not more dense. It's larger. It's a larger part of the ring. And these two will then attract because of the cohesive forces of the ink.
Yes.
They will merge together. So, for example, these will merge together. These will merge together. These, and the number of these parts that will merge together is also a thing that depends on temperature and volume.
Yes, but from one experiment to the other one, you should expect very different results. I mean, you should expect 1, 2, 1, 4,
exactly.
1, 13, 1, 18.
Exactly, and that's what did happen. But we didn't look at that. We looked at the number of generations.
I'm sorry, did they happen or not?
Yes.
Did you observe that? Did you observe like 20 rings?
No, not that many.
What is the maximum number you observed?
I think it was 6.
6. So 6.
You
Even with big drops, it makes
The big
almost
drops,
6.
the big drops didn't do it nicely. The big drops just sort of
fall apart.
yeah, and then when you look at one of the parts that it like broke into, then this part could make up to 6 of these.
Okay, so basically this is some kind of instability of a ring.
Yeah,
Okay.
and it causes it to the cohesive forces just make these bunches of
Well, okay, so
fall down and become new.
okay. So I'd like to go on. I'd like to go on the parameters explanation. What is the role of density?
Okay.
What is the role?
We even experimented with ink that is combined with water, so not 100% ink. So we decreased that delta rho in the equation,
Yeah.
and we obtained fewer fragmentations.
Okay.
But the problem was to work with 100% ink, so we didn't include that in presentation.
Yes, but that wasn't mentioned 100% ink. You have freedom to make it vary, but no problem. Because I think that even with 100% ink, you have a problem with density. Because if you take the first step, okay, you have almost 100% ink at the first step. But when it starts diffusing, and also when you have this drop falling like this, then you have a vortex here, and perhaps it will take water particles into this, and so density here will be lower than density here. So yes, density may vary in the process. So how do you? So that's the problem you.
I think this
How do you
doesn't
address it?
affect it that much, because the point is when the drop starts to it has vortex, but it has around it.
What
This it has a vortex on all sides, and it actually pulls the water from upwards in the middle of it. And you can see that this is why the ring forms. So there's the water doesn't enter that much into the ink.
The reporter started off by mentioning some of the most important parameters of the problem, which was the temperature of the water, the volume of the ink that was dropped in the water, and the existing ink in the water after each experiment, which changes some of the results. After that, he did a qualitative experiment of how the vortices were formed. So he laid out the equations that define the motion and described the phenomenon such as the fragmentation number, diffusivity, and so. And they had a graph about how the fragmentation number relates to the temperature. Now, the opponent said that the experiment was very clear, the explanation was also clear and understood. There was some criticism about some aspects of the presentation, which led to further discussion. For example, they stated that the reporter did not study the evolution of the phenomenon as much as they would have liked, like how the vortex moves through the water. There was no correlation between the experiment and the theory, so there was some theory which was incomplete, and the experimental setup and the measurements, they did not correlate to the theory. They proposed some good aspects that could be discussed further, like surface tension, which was very important, the speed of the droplet as it moves through the liquid, and so on. Now, I would like to move this into discussion, and I would like to ask you, all of you, now you did this in water, is that right?
Yes.
Right. Well, if we change the liquid, for example, let's say we put in oil or we put in a more viscous fluid, what would change? What would be the parameters that would change, and how would the tree develop in another way?
Well, one thing that would change is this delta rho, so the difference in the densities. Also the viscosity of the liquid.
Okay, so I think there's
And discuss.
Yeah, I think there is also something quite interesting in what you mentioned, that, for example, ink is mainly miscible with water. So basically, I think there is no surface tension between ink and water. But with oil, well, I don't know if you did the experiment, but I think that it might not be the case. I think that there is surface tension, and this will prodigiously affect the instability that we mentioned, which is, I think, in literature is called radiator instability. So
that's true, but I think that the point of the problem was to test in water, so that's why we did it.
well, but
that was for further discussion. If you would go ahead.
Yeah, sure.
Yeah. Now, how do you think that the problem would change in the parameters if we changed the initial velocity that we dropped the ink in the water? Like if we did it really fast or really slow, what would change? But the same volume, for example, let's say, what would change?
Well, if I may, sorry. Okay, you have no, don't forget.
So I think we will obtain more fermentations, because I think that there is some correlation between the diffusion of the vortex speed and diffusion of the vortex speed and the speed of the.
Okay. Well, this is a very interesting question, because basically when you have a drop of ink into air, there is surface tension. So there is an energy that is stored to get the interface coherent. When you put it into water, you convert this surface tension energy into something else. So basically it's kinetic energy. But when you change the h of the initial velocity, then you bring more energy. So, well, you expect that the vortex ring will spread more. But if you expect it to spread more, perhaps you can expect more droplets, daughter droplets to be formed. So it's very unclear what will happen next, because if you have more daughter droplets, which are very small, then you may have less generations, because you reduce the volume, so it's a fermentation number. Moreover, but still they can be denser. because they have no time to mix or whatever. I don't know. So to me, it's a very interesting question. It's quite unclear what will happen next.
Okay. Now, you said that you dropped the droplet from outside the liquid.
Yes.
What would happen if you dropped it inside the liquid? Would anything change?
We tried to do that. The problem is that the type of the equipment we used is not sophisticated enough. So if you try to make a drop from a syringe inside the water, it would not wait to make a drop. It would just start falling downwards, and so it's very difficult to make that. That's why we didn't use it.
I think that putting it's what we discussed above, but slightly different. So when you inject a drop, you yourself create the vortex,
Yes.
and so it's the energy that you put in your thumb that gives the initial velocity. So it's very hard to control it indeed. So I don't know.
Yeah. So
So I think basically for purpose of clarity, it's perhaps better to do this in air.
yeah. All right.
Kings may join the discussion, please.
And what do you think would happen? Actually, how do you think you could improve the setup, the experimental setup, so you could actually achieve all of that which you're talking about, like measure the cohesive parameters, measure the speed with which you put in the ink, measurement of the temperature and everything, the radius of the droplets. How did you make this better?
Okay, one about the radius, you could shoot it with a high resolution camera, and you could measure the radius. But we didn't have.
And also, that also goes for the speed.
Yeah, and the problem is that it's really messy when you look at it. So
Yeah.
with a normal camera, it's like
Yeah.
really hard to look at one drop and see its
Yeah.
radius.
I think there was a really good question asked before that hasn't been answered. Why is there a maximum number of generations? Why do the generations stop at some point? Because that's the whole point of the problem.
Okay, so what we found is that after reaching some critical radius, critically small radius of the drop, it just won't divide anymore. It's too compact and stable to make this torus and divide. It will just diffuse slowly.
Yeah.
And if it's too large, at a critically large volume, it will just break off. It won't do anything nice.
Yes, but there is perhaps another idea that if you put very little amount of ink, very small amount of ink in bigger drops, well, it will diffusion time and fragmentation number will be much higher on the very beginning, much higher than the typical instability time. So maybe it's very intricate.
We did that, but we left it out of the presentation because again, the point was ink in water, not ink mixed with something.
Okay.
Yeah, from our references, there is a first article, JJ Thompson. He did a lot of experiments with a lot of different liquids, and also he mentioned that there is boundary delta rho, after which there is no that self-similar fragmentations.
Yeah.
So I think that is like some boundary after which there is no other fragmentation.
Yeah, so basically the boundary with what you mentioned, you have to take into account about the two of us, and perhaps that's why the fragmentation number stays. So that's a bit scary.
Yeah, and could you study, for example, do you think it's important to study the velocity of the drop to the radius of the drop, like if it's in deeper water or in shallower water, or with more velocity, with less velocity? How do you think that affects the levels?
So is your question about those velocities we've shown, or about what the initial velocity is?
About the velocities that you've shown.
Oh, the velocities we've shown are actually just a minute.
Could you answer while they figure
Which exactly? What exactly do?
Well, I mean, you have the velocity of the drop in the water, okay, and that thing expands, and it has a different radius regarding to the depth.
In relativity stability, when you have a denser layer of fluid over a less dense layer of fluid, and you have formation of a drop. So basically, this is where surface tension comes to play, because it has a role which forces the surface to stay minimal. So at the beginning, I think it's forcing the drop to stay into the ring, but when the drop has gained too much importance, then the most interesting thing, energetically speaking, is to break
Yeah, I
it
think
and create the drop.
that doesn't happen here. What
Right, and
happens
that's
is that
precisely doesn't
it
happen.
actually the drop pulls much of the ink with it, and it actually leaves this nice trail. It doesn't like break and cut off.
Yeah, but basically, it's not part of this problem precisely because ink and water are miscible.
Yeah.
But if you make the experiment, for example, with I don't know, glycerol into oil or water, you will get different results. But still, relative thermal instability will occur, I think.
Thank you. Please.
So on this slide there are 3 bullet points out of the 4. The first one is if you put oil and honey, you change the viscosity, then it's initial velocity, and then it's also in the last one spoken about radius. All of these sort of combine very nicely into a number. It's called the Reynolds number. What's the role of the Reynolds number in this problem?
This is quite interesting. Is in you have basically I think the first role we can identify is in the formation of the initial vortex, because you'll have friction friction immediately taking place, and you'll have the droplet which converts its energy of surface tension energy which it had into air into kinetic energy. And so I think that, for example, the size of the vortex and the speed of the inner rolls will be modified by this. But very, very high, very quickly it will be something else. So.
Thank you.
I think that our approach we didn't study that much the Reynolds number and its effect, because we studied just one type of liquid, and we always did the same initial velocity. We just placed the drop on the surface actually. So we thought this approach of just directly looking at specifically ink and water and these effects was sort of more important. Yeah.
Thank you. Let's move on to the next question, please.
As I can conclude from your report, the larger is the volume of a drop, the larger is the number of generations. Do you hope to get infinite number of generations by?
He already stated that there's some critical volume, and at which the drop will just fall apart at the beginning. Gravity is not stable enough.
Yeah, so
It will be really chaotic.
the volume
What
has
is the maximum number of generations you hope to get?
4. That's what we got.
What we got
Not greater than 4?
No. I
because
think we saw 5 in some rare cases, but it was not in all the drops. It was like they did 4 generations, and then one of these drops was a bit larger than the rest and did another one. But that happened very rarely. So basically, if we reach almost the volume at which the drop is very unstable and falls apart in a chaotic fashion, not in this one, it will do 4.
And can you predict this unstable volume?
Well, yes, we probably could. We could measure the. It would depend on temperature also. I think, yeah, and we could predict it from our measurements, but we didn't do that here.
Thank you. Oh, we have another question.
Can I please see in your slide that shows the graph about temperature and number of fragmentations, please? I think the time is in, so I'm going to make the question. And I didn't saw on the last marker of temperature some two markers about the different fragmentation. And does it over there on 6 degrees? There is no circle and triangle. It did split at that volume. What happened there?
Sorry, where?
On the marker of 6 degrees, yeah. It's on the X marker, not triangle or circle.
Oh, the bigger ones were always very chaotic. That's what it was about.
This the biggest one we have. So,
Biggest temperature or?
No, you got the biggest.
biggest drop or the biggest temperature. That's what he's asking.
Oh, okay.
So we have just the biggest, and